Right. So welcome to week 5 of the live session. And today we will be discussing the Mimo channel estimation. So in last class, we discussed the multi-transmitter single receiver antenna setting. And in today's class, we will discuss a multi-transmitter, multi-receiver antenna, which is the MIMO, multiple input, multiple output. And further, we will discuss the channel equalization, why is channel equalization needed in wireless communications. So MIMO by its name, multiple input, multiple output, right? So multiple input means multiple transmit antennas in the input side and multiple antennas on the receiver side. So if you see the diagram, you have a transmitter and it is having, say, uh, some T antennas and transmit antennas. Similarly, you have in the receiver side, say you have R receive antennas. So T transmit antennas are receive antennas. And you should note that each there will be a channel between each antenna of either side. So it will be denoted by H in subscript RT. So here R represents our receive antennas, T represents our transmit antenna. For instance, HR1 means the channel gain between receive antenna R, some general R, and transmit antenna 1, right? So you should note that in this notation, the receive antenna index comes first and then the transmit antenna index comes. OK, so this kind of MIMO system is a R cross T MIMO system. OK, so again, the receive antenna comes first and then the number of transmit antennas, right? So this is a R cross T MIMO system, right? So how will we write the signal received at antenna R, okay, at time K? So this is YRK. So this is antenna R, receive antenna R, okay, and this is our time index, which is denoted with K, right? So what it will be. So just look at this, right? So say what all signals are coming at any general receive antenna R. So it is capturing the signals from all the transmit antennas, right? So it will be some HR1, some HR2, right? So there may be some HR2, right? There will be some HR3 and so on. And we will have to take all of them into consideration. So HR1 which transmits say x1 at time k, HR2 which transmits x2 at time k, similarly HRT which transmits xt at time k, plus VR, this is the AWGN which gets added at receiver R. Okay, so this AWGN is added at the receiver. Okay, this is not due to the channel path, this is due to the receiver noise. Okay. So let us take a simplified case, say for instance, a 2x2 MIMO setup, right? So 2x2 MIMO setup means we have two uh, transmit antennas and two receiver antennas, right? And the corresponding channel coefficients can be denoted as H11, which is between receiver 1 and transmitter 1. H12 is between receiver 1 and transmitter 2. H21 is between receiver 2, transmitter 1, and H22 is between receiver 2 and transmitter 2. So what will be the signal received at antenna 1 of the receiver at some time k? So we can denote that as H11 into X1k plus H12 into X2k plus V1k, which is the AWGN at the antenna 1 of the receiver. Similarly, Y2 of k will be H21 times X1. Okay, and so what it is interesting to note that while the channel coefficients are different, antenna 1 will be transmitting X1k only and antenna 2 will be transmitting X2k only. Okay, at time k. Okay. Similarly, this is x1k. This is also x1k, right? So if we try to represent this system of equations, which we have these two equations in a matrix form. So we can represent this system of equation as y1, y2k. So this is a 2 cross 1. Okay, and then we have this is our channel matrix or the channel gain matrix. So this is a 2 cross 2. And then you have the transmit what you are transmitting. So this is again a 2 cross 1 and plus this is our AWGN, which is again 2 cross 1. So this so since this is at a single time index, okay, we'll see what happens in a multi-time index, what happens. So in general, if you see this is a R cross N, it will be R cross N matrix where N is my number of, this is my number of time instances. Okay, and here we will be having a R cross T matrix. So R is the number of receive antennas, T is the number of transmit antennas. Similarly, this will be a T cross N matrix, and this will be a R cross N matrix, right? So we can represent this vector as a Y vector. Okay, so this will be a Y vector R cross N, R rows and columns, right? So at each column, we will have one time index. Okay. So now we need to compute what will be the channel estimation, right? For this scenario, for this kind of setting where we have multiple transmit antennas and multiple receive antennas. So what to do, right? So we have this equation, right? So y is hx plus v. So this is what we have. And if we take the transpose of it, right? If we take the transpose of it, so y transpose is now hx transpose. So again, we use the property AB transpose is B transpose A transpose, right? So you have X transpose H transpose and V transpose is as it is. So again, so the maximum likelihood in the last class we saw that the maximum likelihood is analogous or equivalent to the least squares, right? This is analogous to the least squares problem. So the least squares will be y minus x transpose h transpose whole square. Okay. And if you just consider it to be of this form y minus xh, and and in the last class we discussed the Moore-Penrose pseudo inverse, right? So it was x transpose x inverse x transpose h. So now if you just try to see the similarity between these two equations, so it is just that each matrix here is having is in its transpose, right? So if you take the transpose of each in this, no, sorry, this is y. Right. So if you just take the transpose of each element, and so this will be h hat transpose, which you will be getting, right? And this will be x transpose transpose x transpose inverse, again x transpose transpose y transpose. Right. So this is still in the form of the Moore-Penrose pseudo inverse, and what we end up getting is that h hat is actually x transpose inverse x y transpose. Okay, and since this was h hat transpose, so if we again take a transpose of this transpose, we get h itself, right? So if you take the transpose of this equation, right, so you will be getting y into x transpose x transpose inverse. So here also again it is notable that the second part of this equation, so this is still our pseudo inverse. Okay, this is still in a pseudo inverse form, The only thing is it has been transposed. Okay. So this is the estimate of a MIMO channel matrix with multiple receive and multiple transmit antennas. So any question or doubt in this MIMO concept? No question? Right. So yes, Yogesh, you can ask. Yogesh, want to ask something?
Yes, sir. Yes, sir.
Yeah, go ahead.
What, sir?
You want to ask something?
No, sir. Has been all clear, sir.
Okay, okay, thank you. So now what is equalization? Right? What is equalization? In this class, we'll just motivate the need for equalization. Just a minute. So, so currently we are studying about wireless communications, right? So our link between the transmitter and receiver is not dedicated, right? So the link or path between the transmitter and receiver is not dedicated. So if you consider a wired communication, say for instance, optic fiber or Ethernet, so you generally have a dedicated cable, right, between transmitter and receiver. And so that is not prone to any attenuations or multipath, right? So it is a dedicated path. But wireless communication is prone to something which is called multipath, and we will see what multipath is. And due to multipath, our transmit symbol which we are transmitting gets affected, and for that we need to perform something which is called equalization, right? So we'll see what it is. So what is multipath? So say you are transmitting something, right? You are transmitting some symbol which you are trying to transmit, and say what you are trying to transmit is kind of it is the line of sight communication, right? LOS is our line of sight communication, and this line of sight communication is blocked, right? So if the line of sight is blocked due to, say, you can have buildings in an outdoor environment, you can have some trees, right? So it is blocked, and the line of sight is, say, or partially blocked, and it is weak, the signal is weak, right? So what happens is that when you do not get a line of sight communication between transmitter and receiver, then it might happen that there are multiple due to natural phenomena of reflection, diffraction, and scattering, multiple other paths get uh, formed for the same symbol which is being transmitted. So just say at time k, right, or if you transmit it, right. So what happens is that the same symbol travels via multiple paths to reach the receiver, right? So earlier we were assuming that there is only a single path, right? There is it's a line of sight communication. So if say this is a line of sight communication, right? It is a direct path between the transmitter and receiver, and the other paths are non-line of sight, NLOS, non-line of sight between the transmitter and receiver. And each of these paths will have a, each path has its own channel gain. Like each path has its own channel gain, say H1, H2, H3, and so on. So some of these paths may be good, right? So some path may be good, some may be bad. Okay, so we don't know. So it might be possible that some of the path. So there is actually something which is called beam forming. Okay, and this is actually an advanced stage of what we are currently studying. So in beamforming, what happens is that you try to exploit these multipaths, or say you have a relay. So you have a primary transmitter, you have a secondary transmitter, and you are trying to steer the beam such that you can beam form at the receiver. Similarly, you can also null form at the receiver. That is called null forming. So there are multiple applications which we do by intelligently exploiting the path laws. But currently what would you know is that each path of the multipath which happens has its own channel gain, right? And it may be beneficial, it may not be beneficial. We don't know that. Okay, and each path also introduces a unique phase shift and attenuation on the original signal, right? So each path will uh, attenuate the signal differently. Each path will have its own phase shift, and each path will also have its own attenuation on the symbol which is being transmitted. So what happens, right? So in multipath, a phase shifted copy of the original signal, okay, happens, and you have such phase shifted copy for each path, right? And it should be noted that the distance of each path is different. Okay, the distance of each path is different. Say for instance, this path has a distance d1, d2. So path 2 has some distance d2. Similarly, path 3 has some distance d3. And due to very different distances of each path between the transmitter and receiver, of how the symbol uh, moves, it will have different time delays, right? So say this has some, so the symbol takes tau1 time to reach the receiver from path 1. If I just name this, say path 1, this is path 2, and this is path 3, right? So it takes a tau1 time from path 1 to reach the receiver. It takes a p2 tau2 time, right, to reach uh, the receiver from path 2. Similarly, it takes tau3 time. Okay, and always note that the distance of line of sight is the shortest path, right? It is the shortest path between the transmitter and receiver, right? Between transmitter and receiver. So the line of sight communication is the shortest path between the transmitter and receiver, and all other paths which will be non-line of sight will have a larger distance. So here, if you see, our path 2 is a line of sight communication, right? And the other P1 and P3 are non-line of sight communication. So D2, that is the distance of line of sight, will always be lesser than the non-line of sight communication. Okay. And due to this, the time taken by the symbol to travel in the line of sight communication will always be the least as compared to other non-line of sight communication. Okay, so say for instance, I am say transmitting an impulse at t equal to 0, right? So what will happen is that at say some t1, I am getting a copy of the impulse which I transmitted. Similarly, at say some time t2, this is I'm getting, so say this is due to path 1, this copy is due to path 2, this copy is due to path 3, right? So we are getting 3 different copies, and each copy is, okay, each copy is differently attenuated, phase shifted at receiver. Okay, so each copy which you receive due to multipath is differently phase shifted, and it is differently attenuated when it comes at the receiver. And always note that the first impulse which you will always receive will be from the line of sight, right, which comes. So all these 3 copies which you are receiving is actually of the same symbol, say symbol 1, right? So you are say transmitting some symbol 1, and of symbol 1 you received 3 copies. Now let's take another example and say instead of an impulse, you are transmitting a square signal, right? So you are transmitting say a square signal. Now, if the medium across which you are transmitting, right? So if we are transmitting, since we are transmitting through wireless medium, right? So our bandwidth can either be narrow band or it can be wide band. Okay, so there are two possible which we generally have, right? So we either have a narrow band communication or we have a wide band communication. Okay, so fine. So what happens is, say we transmit a square, uh, we transmit a square signal at T0, and say at T1, this is my copy due to path 1, this is my copy due to path 2, this is my copy due to path 3, right? So this is what we have due to P1, P2, and P3. And what happens is that all the three copies, when they come at say T1, T2, and T3, they overlap with each other. Right, they overlap with each other. And in a narrow band scenario, when our bandwidth is narrow band, what happens is that these copies are indistinguishable. Okay, so you cannot resolve these different signals. Okay, so that is the problem in a narrow band communication. So what we say is that T3, so if you take this T3 minus T1, so we just consider that all these three indistinguishable symbols are a single symbol. Okay, so that is what we consider in a narrow band communication, and this scenario is called a flat fading model. Okay, now there can be another scenario where say each of the copies which you are receiving due to path 1, path 2, and path 3, right, and they are coming at sufficiently well spaced time between each other so that the copies are distinguishable from each other, and this kind of communication happens in a wideband communication scenario, and in this case it is called a frequency selective fading, right? So we have the flat fading, we have the frequency selective fading, right? So if we have a narrow band communication, we'll have flat fading, and if we have wide band, we will be having a frequency selective fading. Okay, so right. Now, what is inter-symbol interference? Okay. What is this inter-symbol interference? So say we are transmitting two symbols, symbol A and symbol B, right? And say at the receiver, so this is the what you are receiving is say symbol A at path 1, this is symbol A at path 2, symbol A at path 3, and say you receive symbol B of path 1 between uh, symbol A path 1 and symbol A path 2, right? So you are receiving symbol B. So now what happens in this case is that, so at the receiver we don't know, right, that how is this, how are the symbols going to come. So what happens is that either we may consider that this symbol which was actually of uh, B, we can just errorly assume that this was symbol A. So that can be a mistake which we can do, right? So this kind of problem due to the multipath where you have multiple copies of a same transmit symbol, and when they interfere with each other due to the multipath, then it is called inter-symbol interference. Okay, so this is the basic motivation behind inter-symbol interference and why it happens in a wireless scenario. Okay, right. So I think that is all. And so in the next week, we'll see the mathematics behind channel equalization. So if any doubt on channel equalization, and I'll move to problem solving. Okay, any questions? Feel free to ask if you have any question. Okay, so fine. Right. So I'll take the questions. So we have a multi antenna channel estimation, okay, with 10 pilot vectors. So this is a build up to the previous previous year last question, which we discussed in last class. So xk is of this form. So the second row is toggling between +1 and -1, which we discussed in the last week. And and we have y, and the noise variance is 3 dB. And the probability that the channel coefficient lie between within a radius of half. Okay, so let us see what happens. So right, so the probability that you have h hat minus h. So this kind of questions, I believe uh, you are now able to solve. And this is the root of variance, right? And this is greater than half divided by root of variance, right? So this is what we do. And here variance is given as 3 dB. So if you convert variance in watts, so how will you convert variance in watts? So this is 10 to the power 3 by 10. Okay, and this is approximately 1 by 5. So, and this comes out to be 2q root 5 by 4. Okay, you can just check it. It is easy to do. But now what we should remember is that here, if you see the X matrix, right, you have two antennas. Okay, you have two transmit antennas. So what will happen is that, so what we have been asked is that so the probability that estimate of both channel coefficients lie outside a radius of 1 by 2 will be the square of it, right? So 2q. Right. Now what we have been asked is that at least one will lie within this, right? So probability that at least one of the channel coefficient lies inside the radius of half is 1 minus 5 by 4 squared, right? So the answer is A. Any doubts? We'll take the next problem. So we have a multi-antenna channel estimation. We have a transmit matrix X. We have a pilot matrix X. We have a receive vector Y. We have a channel vector H with M parameters. Okay, so and what we are given is that the noise samples are independent Gaussian, zero mean variance sigma square. R is my covariance matrix. So what will be my R? So it will be sigma k square and all zeros, right? And only sigma squares will be in the diagonal, right? So they will all be zeros, right? So you will only have sigma square on the diagonal matrix, right? Okay. And what will be the ML estimate of the channel vector? Okay, so you need to, so I'll solve it. So the channel estimate is computed as X transpose R inverse X inverse X transpose R inverse Y. So what we have basically done is that, so this R actually is my sigma square, and you need to check back the derivation which was done in class. So in that, in class derivation, the sigma square was taken out as a scalar, right? Sigma square I, and the sigma square was taken out. But if the sigma square is not taken out, then it comes in this kind of form. Okay. So you need to go back and check the derivation of say Cramer bound or the next class when the pseudo inverse was derived. Okay, so you can just check those classes and you will see this kind of form. So in that, the sigma square I used to come in the middle and sigma square was taken out as scalar, right? So here we are not taking sigma square out as a scalar. Okay, so so this has these two parts and we'll just solve it one by one. So X transpose R inverse X is actually, so what you have is X of 1 to X of n. Okay, and this is 1 by sigma 1 squared, 1 by sigma 2 squared, 1 by sigma n squared, and all are these 0, right? And you have x1, x2, xn, right? And if you solve this, you will be getting k is 1 to n, 1 by sigma k square, xk, x transpose k, okay? And X transpose R inverse Y is directly 1 by sigma k square xk yk. Okay, so H hat is basically the uh, inverse of this term. Okay, this is separate. So this is 1, this is 2, right? So 1 inverse multiplied with 2. Okay, that is what we need to do. And so this is summation 1 by sigma square k xk x transpose k inverse, and this is multiplied with summation 1 by sigma k square xk yk. Okay, this is what you have. So we don't have to solve this because the answer is given in this form. Okay, this is option B. So now we have to consider the Mimo channel estimation problem. We are given an X vector. So we are given at 4 time indices. Okay. Okay. All right. So we are asked what is the size of this Mimo system. So first you see what is my X vector, right? So if you see my X vector, it is 3 minus 2 minus 2, 3, 4, 2, 2, 2, right? This is what you have. So what is this? So this is my N. N is 4, which is my time index. Okay, this is my time index. So which is denoted by the column. Okay, and the row is basically this is my transmit antenna 1, and this is transmitted by antenna 2, right? So we have in transmitter we have 2 antennas, right? Now let's see what is the y. So now my y is minus 2, 1, minus 3, minus 1, 3, 3, minus 1, minus 2, 2, and okay, this can be minus 3, minus 1, 1. Okay, and we had this. Right now again similar. So here n is still 4, right? Number of time index cannot change. And this is still across the column, right? So this will be receive 1, this is receive 2, this is receive 3, right? So receive we have 3. So what is my MIMO system, right? So this is R cross T, right? This is 3 cross 2. Okay. So this is 3 cross 2. Any doubts in this? No doubts? Right. So question 4. So we have the same MIMO matrix, right? So it is a build up to the previous question. And the pilot matrix X. What is the pilot matrix X? So we derived this, right? Let's see here. Okay, so if you want, I'll do again. So just write each of these time, right? So this is X1, x2, x3, x4, right? And this will be 3 minus 2 minus 2, 3, 4, 2, 2. Okay. So this is what is my X matrix. So this is my pilot matrix. Okay. Any doubts? Right. Question 5. So we have the same problem as in the previous, and what will be the output matrix is what I have asked. So again, Y will be Y1, Y2, Y3, Y4, right? So what is Y1? Minus 2, 1, minus 3 transpose, right? So the row vector becomes a column vector. Similarly, you have minus 1, 3, 3, minus 1, minus 2, 2, minus 3, minus 1, 1, right? So this is, where did it go? Yeah, yeah, C, right? Option C. So, okay, so this is still the previous question. The system model is same. The least squares estimate. So this is what he has asked of the Mimo channel matrix. So let us see, how do you compute the least squares estimate? So h hat is y x transpose x transpose inverse, right? So this is as we discussed before, and it is also done in class derivation, right? So this is for a MIMO system, right? When you have a multiple transmitter system and multiple receiver system, right? So in that case, we have this. So this is option A. Oh, sorry. This is option C. Okay, so you just need to check it out carefully. Any doubts? Feel free to ask if you have any doubt. Question 7, and the system model remains same as we have. And what they have asked is what is the pseudo inverse of the pilot matrix X. So how will you compute the pseudo inverse? So remember, in the previous week we had discussed that h hat is x transpose x inverse x transpose y, and this was our pseudo inverse, right? But this was not for MIMO setting. This was not for a MIMO setting. This was for a multi-transmitter single receiver antenna setting, right? So, and as we saw in the previous question, right? As we saw the, so our pseudo matrix is this part, right? So X. So for MIMO, our pseudo matrix is X transpose X transpose inverse. Okay. So we need to compute this. Right, let's do that. So X transpose is 3 minus 2 minus 2 3 4 2 2 2. Right, this is X transpose, and X transpose. So if we multiply X and X transpose, so 3 minus 2 minus 2 3 4 2 2 2 times 3 minus 2 minus 2 3 4 2 2 2. If you solve this, so what do we have, right? So we have a 2 cross 4 and we have a 4 cross. This is a 4 cross 2, right? So we'll get a 2 cross 2 matrix. Let's do it. So we have 9 plus 4 plus 16 plus 4. Okay. Here we have minus 6 minus 6 plus 8 plus 4 minus 6 minus 6 plus 8 plus 4, and finally second row with second column. So we'll get 4 9 4 4. Okay. Right, and this will give me 33. All right, and this is giving me a 0. This is also giving me a 0, and this will give me, this is 21. Right, and what will be now its inverse, right? XX transpose inverse. So XX transpose inverse, and since this is a diagonal matrix, so 1 by 33, 0, 0, 1 by 21. Right. So now you need to multiply X transpose and XX transpose inverse. And if you multiply them, right? All right. So the good thing is that here we don't. So here this is my X transpose, right? So this is what we have, and this is my X transpose inverse. So option B is the our answer. Any doubts? Doubt? We move ahead. Question 8. So we still have the same problem as above. Right, and they have asked what is the estimate of the channel matrix. All right, so estimate is y multiplied with x transpose, x transpose inverse. Right, so let's multiply it. So what is y? So this is minus 2 1 minus 3 minus 1 3 3 minus 1 minus 2 2 minus 3 minus 1 1. Right, and you have 3 minus 2 minus 2 3 4 2 2 2. This is my y. This is my x transpose, and we have 1 by 33 0 0 1 by 21. This is my x transpose inverse. Right. So now we need to multiply all these three matrices together. So if you multiply all these matrices together, so this is a 3 by 4 matrix. This is a 4 cross 2 matrix. This is a 2 cross 2 matrix, right? So first if you multiply, if I name it 1, 2, 3, right? So if you multiply 2 and 3, we'll get a 4 cross 2 matrix. And then if we multiply 1 with what we got from 2 and 3, so this will be a 3 cross 2 matrix. Have you done some error? Just check. All right, we have not done any error. Yeah, it is fine. So if you solve this, you get minus 44 by 33 minus 7 by 21 minus 13 by 33 1 by 21 minus 5 by 33 22 by 21, and this is a 3 cross 2 matrix. Right, so this is 3 cross 2, this is 3 cross 2. So purely you have to do matrix multiplication, right? So you from the information you need to figure out how to write the pilot matrix, how to write the receive matrix, and then you just need to do the matrix multiplication. Right. Okay. So again, this is the same model. The noise samples are given 0, mean variance is minus 6 dB. Okay. So again, sigma square in dB. is minus 6. So sigma square in watt is 10 to the power minus 6 over 10, and this is approximately 1 by 4. It's approximately 1 by 4. So now we need to find what is the variance of the channel estimate. So how will we do this? So sigma square into x transpose inverse. So this is what we have to compute. And this is 1 by 4. And x transpose inverse we computed above, right? So you just remember this was 1 by 33, 0, 0, 1 by 21. And this will come out to be. So this is 1 over, I believe, 132, 0, 0. And this is 84. Okay. So if you see, so this is my variance over H1. Okay. And this is my variance over channel H2, right? And this is my cross variances, which are 0, right? That is the both the channel are independent to each other. So 1 by 32 and 1 by 84. So this is the answer. Any doubt? Right. So we move ahead, and final question, what is channel equalization? So as we discussed, so channel equalization. So why do we do channel equalization? So if you have a transmitter, right, and if you have a receiver, and due to the wireless medium, we have multiple paths, right, between the same transmitter and receiver. So we have, say, if you are transmitting a impulse, right, so each impulse have different copies of the same transmit symbol are uh, generated for each path, and they add up at the transmitter. And so basically they come at different time intervals, right? They come at different time intervals, and they can have different uh, they will have different phase shift, and they will have different attenuation. And so this is what is the and say you are having another symbol. So this is A and this is B. So there can be a possibility that you have copies of A, and you also in between have a copy of B, right? So when you have this kind of stuff, so this is called inter-symbol interference. And to remove this inter-symbol interference, we have to do what is called channel equalization, which we will see in the next week, right? And so this is the answer, removing the effect of ISI. Okay. So any doubt up to here? Any doubt to anyone?
No doubt, sir.
So I think then that ends the discussion for this week. Yeah, someone is raising hand. So please go
Yes,
ahead.
sir,